Okay, guys, so we're going to talk about how to solve a linear differential equation in this form. So, as long as you've been seeing in the notes, most of you guys already remember that the form of a linear differential equation is just y prime, which could be written as dy by dt, is equals to a minus by. So, when you have that kind of form, the standard solution that's given out to you in the books, or you can just literally take up the values of a, b, and the initial condition y value, and you can plug them all in here and you have the solution right in front of you. But what is the actual way to get to a solution? Because this formula might not work when you switch them around here and that side. So let's say you have an equation that's not like this, or something like by minus a. Of course, you can rearrange it to make it look like the one that you already know. Or let's just talk through the methodology of how you solve these kind of equations. Okay, so there's an example that I'm going to solve. Let me just pull that over in a second. Yep, so the example that I have is that y prime is just equals to 0.2y minus 4. Given with the initial condition, that's 48. So let's try to solve this. The very first step in actually solving this differential equation is what you assume your y prime to be something called v. Okay, so essentially what you have is that v is just 0.2y minus 4 because you just said that y prime is v. So now when you have that equation, you take a derivative of that equation with respect to time. What you're supposed to get is v prime equals to 0.2 y prime minus 0. Or essentially, v prime equals to 0.2 y prime. Okay? So now remember, we called y prime as v. We can substitute it back in. So now our differential equation is a very standard equation right here in front of you. So in this case, you know, whenever you're given an equation like this is the fundamental solution of an exponential differential equation. Okay. In this case, what you do is these equations will always have exponential functions, and this is going to be just the rate. So from this point onwards, you can jump up straight to v function is just going to be the initial value of v naught e to the power 0.2t. Because you know this is a standard form. Whenever you have a function like this, I'm going to write that as a fact inside. So the fact is, if you have dy dt equals to ky, then y equals to y naught e to the power kt is a solution. How do you know this? This is because of the facts that we already talked about in the previous chapter when you had exponential growth and exponential decay. Okay? So that's just a fact that we're going to mention over there. Now we were at that spot. What I'm going to do is I'm going to get rid of this. And I'll come back to our work. So the work here again is going to be when you have the solution. So now in this case, you want your equation to be in terms of y. Okay? You know the v that you chose is just that number, so you can plug it in there. And let's see what it becomes. So now you have 0.2y minus 4 equals to some initial value of v e to the power 0.2t. So now what's going to be the initial value of v? The v naught value is just going to be whatever the initial value of y naught is going to give you in this equation. So 0.2 y naught minus 4, because it's the same equation here. Okay, so these are the two values. When you plug them in, what you're going to get is 0.2y minus 4 equals to 0.2y initial value minus 4 and e to the power 0.2t. So now from this, when you isolate it for y, what are you going to get? We'll move the 4 on the right side. So you're going to have 0.2 y naught minus 4 e to the power 0.2t plus 4. This should be 0.2y. And now when you divide both sides by 0.2, your answer should look something like this. So 0. Divided by. And now you plug in the given value that you have here as 48 into this, and your final solution should look something like this. So I'm going to simplify this a bit. This could be written as y0 minus 4 divided by 0.2 e to the power 0.2t plus 4 divided by 0.2. So what I did is just like put them separately in those things. And 4 divided by 0.2 could be easily calculated. Let me just see what that number is, just double confirm. So that's 20. So this number is just going to be 20. And now my y0 value is 48, so let me just plug all of them in and make it a final solution. So your y is going to look like 48 minus 20, so it's going to be 28, e to the power 0.2t, and then plus 20 again. And this is how you get to the solution, actually, from the differential equation using a method. Okay, the thing that you learned before, where you just like literally just pick out the a and b values and plug them in, is also found using the same procedure here as well. You can treat both of these constants as a's and b's in some initial value, and you can solve it expression wise. You're gonna get the same result. And